Welcome to this explainer. Think of today as our practical lab session. By the end of this walkthrough, you're going to be able to look at a piece of network hardware and instantly identify and categorize its physical terminations. It's an absolutely crucial skill, honestly. You really have to know exactly what hardware you're dealing with before you even touch a configuration screen, because this physical layer, this is where all data transfer actually starts. All right, let's jump right in. To get our setup right today, we are going to walk through 4 main categories. Number 1, optical terminations. 2, wireless antennas. 3, traditional copper terminations. And 4, modular transceivers.
All right, Section 1, optical terminations. We use these to carefully terminate really fragile fiber optic cables. Look closely at the visual contrast here. On the left, we've got the ST, or straight tip connector. Notice how it's perfectly round? The tip is literally straight and cylindrical. Now compare that to the right side, the SC, or subscriber connector. It's got this blocky, square housing. In the lab, the most common mistake students make is trying to just jam the wrong shape into a patch panel. A correct connection will seat incredibly smoothly and sit completely flush. If it physically won't slide in, back up and check your geometry. Never force it. If you do, you risk shattering the glass core inside and you'll have to start all over.
Next up, check out the smaller LC, or local connector, on the left. It has this very distinct little latch on top. Contrast that with the MTRJ connector on the right, which is super compact and blocky. Now, why does that LC latch exist? It's specifically there to lock the fiber into high-density panels, where space is at a premium. It prevents accidental disconnects when you're reaching into busy server racks. The procedure here is simple. When you push it in, listen for a very clear, audible click. If you don't hear a click, it's not seated right, and your light pulses simply won't make the jump across the gap.
Okay, Section 2, let's move on from fiber optics and look at the threaded hardware used for wireless antennas.
Check out the heavily ridged metal collar on the RPTNC on the left. Those thick ridges are there for a reason. They give you a physical grip so you can tighten it by hand. Now look at the smaller, gold-toned RPSMA connector on the right. Notice how it has a smoother, hexagonal shape? That's because it's meant to be tightened with a wrench. A really frequent error we see is trying to thread an RPSMA antenna onto an RPTNC post. You'll know you have the right fit because the metal threads will spin on immediately and smoothly. If it starts binding up, feels loose, or resists turning, stop right away. You've mismatched them, and you're going to strip the threads.
Moving into Section 3, copper terminations. These are the traditional interfaces connecting everyday workstations. This is a classic lab mix-up right here. On the left, we have the wider RJ45, which is built for data networking. Next to it is the narrower RJ11, typically used for analog phones. Because the RJ11 is narrower, it is way too easy to accidentally plug a phone cable into a network wall jack. Here's how to tell he messed up. If your cable slides in but wiggles loosely from side to side, you've used the wrong one. The RJ45 has to be wider because it holds more copper pins. It needs those extra pins to handle complex data transfer, whereas a basic analog phone line really only needs a couple.
Now, when you step up to high-density telecommunications gear, you'll see this massive, elongated RJ21 connector. Look at the sheer length of that black plastic head. It's engineered to secure a giant 25-pair cable. That means 50 individual copper wires are terminating securely into one single block. You'll see these bridging older voice systems to modern networks. The trick to getting this right, you have to perfectly align the entire length of that connector before you even try to press it in and secure it.
Here we are looking at older serial and parallel connections. You've got the 9-pin female DE9 on the left and the much wider 25-pin male DB25 on the right. A successful termination here means flawlessly aligning those tiny physical holes on the female side to match the protruding pins on the device. It's a delicate procedure. If you get impatient and try to force it, you're going to bend a pin, and a bent pin means an instantly failed termination. Take your time and make sure every single pin slots in straight before you tighten those anchor screws.
And for complex router setups, you step up to this high-density male DB60 interface. Look at that massive concentration of gold pins packed inside that blue metal casing. It's designed this way to carry multiple data streams through one heavily secured point. You'll mostly be using these to connect enterprise-grade hardware across wide-area networks.
All right, final category, Section 4, modular transceivers. These slide right into empty slots on networking gear.
Here are 2 standard GBICs side by side. On the left, you can see the empty square slots for a fiber optic module. On the right is a copper-based module with that familiar built-in RJ45 port. The whole reason we use these is for flexibility. In the real world, you can hot swap these sliding modules in and out to perfectly match whatever physical cable type you need for a specific run. You just slide it in rather than having to buy and replace an entirely new network switch. It's a really practical setup.
Now this one is really interesting. This unique transparent block is a Cisco's GigaStack. It's a proprietary GBIC, and we use it to physically stack multiple network switches together so the system treats them as one single logical unit. Notice how you can visually inspect all the internal metallic components right through that clear plastic casing? That's not just for looks. It lets you quickly identify if any internal damage or burning has happened to the termination over time.
Now, SFPs. These serve the exact same modular purpose as those standard GBICs we just looked at, but they do it in a significantly smaller form factor. Look at those sleek metal housings. Again, we've got a module built for fiber connections on the left, right next to a module built for a standard copper RJ45 connection. A huge mistake people make in hardware provisioning is buying the wrong form factor for their gear. You always need to check your equipment documentation. Does your switch require the larger, older GBIC shape, or does it take these modern, smaller SFP modules?
Lastly, take a look at the X2 module. This is a much larger, much more robust transceiver, and it's built specifically for massive 10 gigabit network speeds. See those heavy metallic ridges along the top? Those are heat sinks for thermal dissipation. Moving data at 10 gigabits generates a lot of heat, and this bulky design keeps the hardware from actually melting down while it provides a secure endpoint for those high-speed fiber cables.
So to wrap up our lab session, I highly recommend checking out the full source document to study this catalog in more detail. Next time you look at the back of your office router or even your home gear, really look at it. Ask yourself, if just one of these tiny, specific geometric shapes fails to seat perfectly, what happens to all that data trying to cross the globe? The entire functioning internet relies on these exact physical terminations aligning flawlessly. Are you absolutely sure you know which one you're holding?